In this video, I want to do a little calculus here with Mathcad. So this is a problem you also often run into in foundation engineering where you have a flexible foundation that's in the form of a square of a rectangle, and you're looking to find the change in stress at some point beneath one of the corners. So Boussinesq came up with this equation that says that the rate of change of the vertical stress is equal to this equation of the x, y, and z coordinates. And then I think in like 1935, Newmark figured out how to calculate this with some variables that we'll show here in a minute. But the idea is that if you take the integral of both sides of this equation, then you get a integral evaluated from 0 to x and 0 to y that will give you the change in stress as a function of q and the xyz coordinates. So I thought I would do this problem using Mathcad and just using the calculus portion of it, and then I would go through another type of solution using the Newmark evaluation. So let's put in some of our givens here. So Q is equal to 50 kilonewtons per meter cubed, squared. And this came out of DOS Advanced Soil Mechanics, 3rd edition. So Q is 50 kilonewtons per meter squared, or 50 kilopascals. So in this particular problem, we have a rectangle, and we want to find the area or the stress at a depth of 3 meters below point A. And so point A is 4.5 meters in the x direction and 1.5 meters in the y direction. So I'm going to need two L's. I'm going to need a L1, which is equal to 4.5 meters. And I will need a B1, like that, a capital B, which is 1.5 meters. And then I'll need an L2, which is 1.5 meters, and a B2, which is 1.5 meters. So the second little area is a square. Okay, so now I've got what I need. So let's go down here and create an integral. So I'm going to, instead of call it sigma, I'm going to call it delta sigma. So I type in D, I need to do a capital D, Control G, and then S, Control G, Shift semicolon, and now I need to go up here to my operators, and under the calculus area there, I'm going to type in this integral. And I'm going to need two of them because this is really a double integral because I have to integrate it in the x direction and in the y direction. So let's do both of these. That didn't work. I didn't have my cursor in the right spot. Let me hit undo. Let me put my cursor where it needs to be, and now I can insert another integral sign. There we go. So the first one is going to be from 0 to B1, capital B, Control underscore 1. And the second one's going to be from 0 to L1, Control underscore 1. So let me type in, I'm going to do some other manipulations here to make this problem work, but let me just get this integral in. So this would be 3 times Q times Z cubed dx dy. And then I use my space bar to tab over so that I can get a quotient there. So this will be 2. You don't have to hit the multiplication key. You can just type in 2 pi, and there's a little implicit multiplication in there. You don't actually have to calculate it, or I'm sorry, you don't have to actually express it. So times And then I'll use the parentheses x squared plus y squared plus z squared, and then I'm raising this whole thing to the 5/2 power. Okay. So I haven't specified z, so it's let me know I've got an error, so I need to let it know that z is equal to 3 meters. Okay, so it looks like it's going to do something, but this doesn't really solve the problem. I've got the integral set up like it should, but I don't really have the problem solved, because what I have to do is that I have to figure out the change in stress under one of the corners of this rectangle, plus the change in stress underneath this one, number 3, plus the change in stress in 4 and the change in stress in 2. So 2 and 4 are the same size, 1 and 3 are the same size, so I can figure out the change in stress at each of these two different areas. So one will be a rectangle, one will be a square. So this would be 2 times, got to get my cursor in the right spot, 2 times plus, and I need to do the whole thing again. So I'm going to put in 2 integral operators and then make sure I put my cursor where it's supposed to be the second time around. There we go. And then I'm going to copy this, Control C, and then I'm going to paste it, dx dy, and then I'm going to multiply this times 2, and then I'm going to put my limits of my integration in correctly. Go from 0 to, this time it'll be B2, L2. Then put the control underscore 2 there. All right, so I didn't get an error message, so I think it's probably computed something. It says I'm missing something here. Oh, it's expecting, I've got some little glitch right there that I need to fix. It's expecting some square value there. There we go. So this is in kPa. All right, so I've got the answer to the problem is 21.538 kilopascals. Excuse me, or kilonewtons per meter squared. So that's pretty awesome, but the question is, well, how do I know it's right? You know, how would I go about checking this? Well, one way is that you could go back in and look and make sure that you've got the limits of integration right. Okay, and this is 2 times that. I've got 2 of these long ones and 2 of the short ones. This is the long one, this is the short one. I've got my limits from 0 to B1, this one's 0 to B2. Yep, it should be right. But if I wanted to, I could go back in and use the numeric method to go ahead and check this. So let's do that. So this may look familiar too. I went ahead and cut and paste this from DOS. This was an example problem that he had solved. So a lot of times you see this problem set up as the change in stress is equal to the foundation pressure, surcharge pressure, times a influence factor, and the influence factor is a function of these values m and m, where m is a function of b1 and z, and n is a function of l1 and z. And so what I did was that, and again, this is not too difficult in Mathcad. You can type these things in and then you can check, and yeah, I've got the right numbers in here. Okay. It would be a little tough to do in Excel, because think of what you would have to do in Excel. You'd have to have all these different values. You'd have to code it correctly, and then debugging it would be an issue, because you really couldn't see if there was a one-to-one correspondence between the formula that you saw in the book and what you're typing into Excel. But here in Mathcad, you can see that there is a one-to-one correspondence between the formula in the book and the way I typed it in Mathcad. So when I did the long one, the influence factor was 0.131. When I did the short one, the influence factor was 0.084. And then when I multiplied them out, so I multiplied it times the surcharge pressure times twice the long one plus twice of the short one, the influence factor, and I get 21.538, which is exactly what I got when I did this. So this is a really good example of how to use the numerical integration techniques built into Mathcad to very quickly and easily solve a problem that has a solution that's easy to check and compare to book solutions, so that you have confidence in what you're doing. Plus, again, when a reviewer sees this, it just looks very nice and professional, and it makes you look like you really know what you're doing and what you do.